So we focus on allegedly safe libraries that rely on internal use of unsafe code. And our main motivation for this is the Rust programming language. So Rust offers a type system that statically ensures memory safety, making it a safe alternative to C, C++. So although Rust does provide a way of performing low-level unsafe memory operations, it still ensures memory safety through the use of safe abstractions. Now, for example, here we have an abstraction of even numbers in Rust. So we assume there's a user-defined even type. And we have three functions. We have a zero constructor that basically wraps 0 as something of type even. We have a successor function that receives something of type even, increments its value, and returns it as something of type even. And we have a next function that receives an even number, increments the number twice, and returns it as an even number. Now, as you can see, the successor function doesn't really respect the abstraction that we want for even numbers. So the type of the function is marked as an unsafe function. And when we look at the next function, since it uses the successor function, it wraps its usage as inside the unsafe block. But the next function itself is a safe function because it's using this unsafe successor function in a safe manner by calling it twice in a row. So this is what I mean by using safe abstractions to basically encapsulate usage of unsafe code. And we can say that this is a safe abstraction for even numbers because as long as we interact with this library using only safe functions, then we are guaranteed to never break the assumptions that we can do on elements of the type even. So, for example, I could define this naive function that receives an even number, and then it basically checks the remainder of the division by 2 of whatever it was passed as an argument. If the remainder is 0, then it's an even number and it does nothing. If it's 1, then it will unsafely perform some operation that results in undefined behavior, like division by 0 or performing a double free. Now we can be sure. Now the naive function is marked as safe, and we can be sure that the function is safe to execute as long as we only use safe functions from our even library. And we can ensure this even though we have usage of unsafe code inside, because it will never reach the if block. And this is the main idea behind the type system in Rust, that the type signatures in Rust actually encode specifications. So, and we can do so by basically restricting the inputs that the function takes by assuming that as long as we have well-typed inputs, the function will execute safely. If, for example, we were to consider the successor function as a safe function, then this would no longer be a safe abstraction because it breaks the assumptions that we are trying to make about the even type. So the naive function would be able of exhibiting undefined behavior, even though it is marked as safe. Now, what's special about Rust that we don't have, for instance, in C language is precisely this treatment, this separation between safe and unsafe code. So this here is an equivalent C code to the abstraction that we have for the even type. It's mostly identical to the unsafe abstraction in Rust. And the key idea here is that in C, since we don't have this notion of unsafe functions, every function in C is assumed to be an unsafe function. So we cannot just look at the type signature and say that the naive function is incorrectly typed because it will exhibit it might exhibit undefined behavior. The C type system always allows that to happen. In C, the only function that is enforced to be safe is considered to be the main function. So if we want to find these kinds of bugs, we need to consider that there exists an executable trace that starts from the main function and eventually calls the naive function with an incorrect input. So to sum this up, the idea here is that in Rust, when you have a safe function, as long as we have well-typed inputs, we will never have undefined behavior, or we should never have undefined behavior. And in functions in C, they're by default unsafe, so undefined behavior is always possible. So we can't really we can't prove these kinds of bugs looking just at the type of a function. So what this means is that while in C we have, for us to detect these sorts of errors, we need to have an executable path from a main function. In Rust, we can look at functions isolatedly, and we can report errors as a type unsoundness for that given function. So we don't really need a code base as we need in C to verify to show that these bugs exist. We can actually find these bugs in arbitrary Rust libraries. And for those who are familiar with the term, this basically means that the notion of manifest error is much larger in Rust than it is in C. And so, in terms of reasoning about these allegedly safe libraries that rely on internal use of unsafe code, there is known work in terms of verification. So to show that that the safe encapsulation is in fact correct. So there's both automated and foundational approaches. Most notably, Rust Belt provides a framework to perform machine check proofs in the ROC proof assistant for these kinds of cases. All of these are consist in correctness proofs using Hoare logic or derivatives. And therefore, these approaches are over-approximate, and they rely on type invariants that are basically a semantic interpretation of what it means for a value to be of a given type. And these type invariants must be user-provided. Now, in terms of refuting the safety of these allegedly safe libraries, because there's no guarantee that they are in fact safe, there is no known work about this, and this is what today's talk is about. So I'm presenting our approach, Ruxt, which fully automatically detects these types of this kind of type unsoundness in allegedly safe libraries. Our approach presents proofs of incorrectness using incorrectness logic. And instead of relying on user-defined annotations and type invariants, we work with under-approximate type spaces, where the main idea of the approach is to infer well-typed terms for a given type. So I'm going to give an example, more concrete example. So let's consider the unsafe abstraction in Rust, where we consider the successor function to be a safe function. So here the idea is we have the blue box that represents the type space for the type even, and we're going to symbolically execute these functions to try to populate this type space. So the zero function doesn't receive any arguments, so we can symbolically execute it, and since it's a safe function, its output type, whatever it outputs, must be of the type even and must satisfy the even invariant. So we know that 0 belongs to the even type space. And since 0 is a well-typed instance of the even type, we can provide it as a well-typed input for other safe functions. We could provide it as input for the successor function, and we would know that it's, after executing it, we would know that 1 must be of the type even. We could pass 0 to the next function and see that 2 is also the type even, and we can continue for as long as we want. Now, this also means that for the naive function that is supposedly safe, we could provide any well-typed input, and the naive function will execute safely. But as we have seen before, if we provided an odd number, then the naive function will result in undefined behavior, which by the type signature should never happen. So we have shown that there is a type unsoundness in our library because basically what happens is that we can only with safe calls to the functions in our library, we can actually construct a program that results in undefined behavior. So we've seen that example. We can construct this program as well. We first learned that 0 is something of the type even. Then we call next, and we learn that 2 is of type even. We call the successor function. We know that 3 is of type even. So the naive function will exhibit undefined behavior for 3. We could have a similar program where we switch the successor, the order of the successor and the next function, where we first infer that 1 is of type even and 3 is of type even, and both of them will result in undefined behavior. And the important thing to note here is that although we have proven that there exists a trace in a library, that the safe trace in a library that will result in undefined behavior, we are not exploring the space of all possible traces. So in these two examples, right before we reach the call to the naive function, in both partial traces, we infer that 3 is of type even, but we do not explore the traces from there. We don't, so we don't go from the first partial trace and branch out from there, or try to branch out from this from the other program. In both programs, we managed to learn that there exists they learn the same instance, that 3 is of type even, and we test out on that inferred instance. So this is to say that our approach shortens the exploration space, which we expect to be an important factor in terms of the scalability of our approach in the future. So looking into the actual algorithm, so we start off by initializing an empty context for the type spaces, which we call sigma here. And then we pick some safe function from our library and some well-typed inputs from what we have learned so far. We symbolically execute the function for those inputs, and if we get undefined behavior, then we manage to refute safety of the library. If we have no undefined behavior, then that means that we learned a new instance of the type, so we can update sigma accordingly. And we repeat to the second step to pick another function. The algorithm terminates either when we get undefined behavior or when a limit is exhausted. So this means that we can get false negatives. So some type unsoundnesses may not be found, but we obtain no false positive guarantee, which means that every refuted type that we get is evidence of a type unsoundness in a library. Yes, and at this point, we have a prototype implementation in OCaml for a very simplified version of Rust, which we call Lambda Rust, since we are mostly inspired in the Lambda Rust language by Rust Belt. We don't handle any references yet, which is an important thing about Rust, but it is part of our roadmap. We have a full formalization in Rock of the semantics of our Lambda Rust language, as well as the logical framework, which includes basically a simplified version of Rust Belt and an incorrectness separation logic and properties relating both kinds of reasoning. And we have a partial implementation of the algorithm itself, though the interesting properties that we want are still a work in progress. And do I still have a minute or two? Okay. So I'm going to quickly just show a demo.
Bigger, please.
Bigger, okay. Maybe too big. Okay, so basically I have here an embedding of our even example using our Lambda Rust language, but in OCaml. So here we have the 0 function, we have the successor function, we have the next function as well, and finally we have the naive function. And down here we have our algorithm, find unsoundness, that basically if we run the algorithm, it found no unsoundness because I set the successor function as an unsafe function, which makes sense. If it's unsafe, then there is no unsoundness to be found. But if you make the function safe, then the algorithm found the unsoundness, and so we can be sure that, and like I said, this is a true positive. It's a guarantee of the algorithm, so yes, that's basically what I wanted to show you. So yeah, thank you for having me.
When you say symbolic execution, it's on the types?
Symbolic.
When you say symbolic execution, it's on the types?
I mean, we don't really handle types, or better yet, the types, we only have a name for it. So we symbolically execute, like we have the state, we execute it, get the state, and then we learn that whatever state we get at the end must be something related with the output type itself. Okay. That's the idea. Okay.
Any questions? I have a question.
Yes.
You say if you find a problem, then it's because there's an unsoundness in the library. But
Yes.
it could be, I have trouble figuring out how you delimitate the library versus the rest. Like it could be a problem in some other library that's unsafe and exposes unsafe types somehow.
Yeah.
Like if, okay, so there's a problem somewhere.
With that
Yeah,
effect.
yes.
Hi, thanks. That sounds like a fun tool. So do you have, I don't know, ideas or plans for finding bugs that only arise when you combine two libraries which are correct in isolation, which is a particularly fun kind of thing that sometimes happens?
This works with different types. So basically what's going to happen is that you populate those two types. And since you're only handling safe functions themselves, like if you find undefined behavior at some point, it means that there exists an error somewhere. We don't know, you don't know which type it is, but this generalizes for more than one type, if that answers the question.
Okay, so is the plan like that the standard library types might be axiomatized in or something, because I can use those as well? Right, like, I don't know, maybe a library uses vec of even or something, and now it's relevant what you can do on the vec. And things like that.
Yes. Not sure how to answer that question. Do you have any idea?
Vec and we generate the spec of vec. You can just do that same thing on vec and get what a vec is.
Right, so this would be like the tool would come with these descriptions or something, is the idea.
You just run it on the standard library,
right.
And it would infer the type space for vec.
Right, but I would have to run it on my library combined with the standard library. But
well, we would, yeah, probably pre-run it or something.
yeah. Okay, cool, thanks.
Okay. Another. There's more people there. Yeah, it's fine.
So I want to ask the question that I thought Ralph was going to ask, which is, so with the sort of Rust Belt work, they found bugs in the unsafe library.
Yes.
Now, have you got enough that you can find those bugs, or is there other technology that means like higher order or something that you're not there yet?
I mean, I'm not entirely sure. Like, I mean, we don't since we don't handle references. There are a lot of bugs that we can't find. For instance, I think iterator invalidation. That was one of the errors that they managed to find. Like, that's something that you need to handle. Reason about references, I think. Not, yeah, but yeah, we haven't looked at actual examples that they managed to prove in the. Actual errors that they found in the standard library, we just came up with like these simple examples that we managed to find. But that is something that we plan to.
No, it's a great pathway.
Yeah. Yes. Okay.
Thanks.
For that, okay. Okay. Yeah, more trickier. Okay. Yeah. Yes.
Time for our next talk. So thanks again, Pedro.
Thank you.